Hello everyone, welcome to the lecture session on tribology of 7th semester mechanical engineering. Today as we are seeing module 4, that is hydrostatic bearing, we will continue our discussion on the problems. So today we will start with one more problem of hydrostatic thrust bearing. The problem goes like this: the hydrostatic thrust bearing has the following characteristics. Hydrostatic thrust bearing has the following characteristics. First one, the load, the vertical thrust equals 60 kilonewton. Vertical thrust equals 60 kilonewton. Diameter of the shaft is 500 mm. Diameter of the shaft is 500 mm. Diameter of the pocket is 300 mm. Diameter of the pocket is 300 mm. Viscosity of the lubricant used is 35 centipoise. Viscosity of the lubricant used is 35 centipoise, comma, oil film thickness is 0.01 mm. Oil film thickness is 0.01 mm. Full stop. Determine the oil flow through the bearing. Second sub question, the power loss due to viscous friction. The problem, I will repeat the problem once again. A hydrostatic thrust bearing has the following characteristics. The vertical thrust 60 kilonewton, comma, diameter of the shaft 500 mm, diameter of the pocket 300 mm, viscosity of the lubricant used is 35 cp, comma, minimum oil film thickness is 0.01 mm. Determine the rate of oil flow through the bearing. Second sub question, power loss due to viscous friction. So based on the problem statement, let us write down the given data as we have done in the previous problems. So vertical thrust means it is the vertical load that is acting on the bearing, that is W, which is equal to 60 kilonewton. Diameter of the shaft D2 equals 500 mm, which is nothing but 0.5 meters. Diameter of the pocket D1 equals 300 mm, which is nothing but 0.3 meters. Viscosity 35 cp and which is can be taken as 35 into 10 power minus 3 Pascal seconds. Oil film thickness is 0.01 mm and we have converted that into meters as 0.01 into 10 power minus 3 meters. So they have asked us to find out the rate of oil flow, that is Q, and the power loss due to viscous friction. So we know the expression of Q. Let us start with our problem. So to find the value of Q, or rate of oil flow, through the bearing. We know the expression of Q from our data handbook, that is page number 23.67, equation number 23.144, which is nothing but pi P naught H cube divided by 6 neta natural log of D2 by D1. Equation number 23.144, page number 23.67. This is the expression that we have taken down from the data handbook. Now please look into this equation where Q is the unknown that we need to find. P naught is a supply inlet pressure which is not known to us, which is not mentioned in the data provided in our problem statement. Minimum film thickness is known to us, viscosity is known, diameters of the pocket and the shaft are known. The only unknown is P naught. So without knowing the value of P naught, that is the inlet supply pressure, we cannot proceed this problem. So what we should do? Let us find out the value of P naught first, Then after getting the value of P naught, let us resubstitute that value of P naught into Q, expression of Q, then we can easily find the value of Q, that is rate of oil flow through the bearing. So how to find the value of P naught, that is inlet supply pressure? Again, we have a data equation provided in our data handbook, that is from data handbook, P naught equals 8 W, W is known to us, natural log d2 by d1, we know the diameters, pi d2 square minus d1 square, d2 square minus d1 square. Equation number 23.142a, page number 23.67. 23.67. So this is the equation where we know all the values of this equation. Let us substitute this value and get the value of P naught. 60 kilonewton, 60 into 10 power 3, natural log d2 0.5, d1 0.3, pi 0.5 square minus 0.3 square, 0.3 square. So let us calculate. Let us calculate it. We get that as 0.487 into 10 power 6 Newton per meter square, or we can also write that as 0.487 megapascal. 0.487 megapascal. Now we know the value of P naught. Can we substitute in the expression of Q? Q pi into 0.487 into 10 power 6 H .01 into 10 power minus 3 whole thing divided by 6 into the viscosity is 35 into 10 power minus 3 into natural log d2, that is 0.5 divided by d1, that is 0.3. Pi into 0.487 into 0.01 divided by 6 into 35 minus 3 divided by pi P naught, sorry, we have forgotten the H cube. So I was just worried what is this value. Pi into 0.487 E6 into 0.01 E minus 3 cube divided by 6 into 35 E minus 3 divided by natural log of 0.5 divided by 0.3. So we get this as 1.426 into 10 power minus 8 meter cube per second. Meter cube per second. So we have found the first unknown that is asked in our problem. Let us move to the second sub question, that is power loss. Power loss due to viscous friction is given by P mu. P mu equals, we have an expression in our data handbook. We have an expression in our data handbook as 0.062 n dash square neta divided by 16h d2 to the power of 4 minus d1 to the power of 4. 23.145 A divided by, page number 23.67. So I had forgotten one particular value here. The speed that is at which the shaft is running is assumed to be 600 rpm. So the n dash value will become 600 by 60. We will get that as 10 rps. Without the speed, we cannot get the power loss. Without the speed, we cannot find out the value of power loss. So we know all the values of this power loss expression, and the only thing that we are left out with is the substitution part and get the solution. So we know n dash square, we know the value of neta, we know the value of h. Shall we calculate now? P mu 0.062 into 10 square into neta. Point 0.5 to the power of 4 minus 0.3 to the power of 4. Into 10 square into 35e minus 3 divided by 16 into 0.01. We get this as 73.78 kilowatts. 73.78 kilowatts. So they have asked us to find out the oil flow rate or rate of oil flow through the bearing and the power loss due to viscous friction by giving some of the values like the vertical thrust, diameters and viscosity and the speed. So to get the oil flow rate, the only unknown we had in our equation was the supply pressure. We found out the supply pressure at the first instant. Then once we got the supply pressure, we substituted the back that supply pressure value into our oil flow rate expression available in the data handbook. We got that oil flow rate as 1.426 into 10 power minus 8 meter cube per second, and then we got a power loss due to viscous friction. So this is the problem that was asked to solve. See, the problems are quite simple, as we have seen from the first problem till now. We have used only 3 equations available in the data handbook, that is flow rate, pressure and the power loss. So this is how the problems will be, and along with these problems, as I am continuously stressing this, you will be getting the expression, that is derivation of either the load carrying capacity or the oil flow rate. That is, either you will have asked to derive for Q or you will be asked to derive for W. Okay, let us move on to the next problem now. Let us move on to the next problem. A hydrostatic step bearing has the following characteristics. A hydrostatic step bearing has the following characteristics. Diameter of the shaft 130 mm. This can be written as 0.13 meters, diameter of the shaft 130 mm, comma, diameter of pocket is 55 mm, diameter of pocket is 55 mm, shaft speed is 1800 rpm, shaft speed is 1800 rpm, comma, inlet supply pressure is 3.75 megapascal, 3.75 megapascal, external pressure equals 0, the mean oil operating temperature is 60 degree centigrade, the oil used is SAE 20, full stop. The desirable oil film thickness is 0.0875 millimeters. Desirable oil film thickness is 0.0875 millimeters. Determine the load that can be supported by the bearing. Second sub question, oil flow rate through the bearing. Third sub question, power loss due to viscous friction. I will repeat the problem once again. A hydrostatic step bearing has the following characteristics. Diameter of the shaft 130 mm, diameter of a pocket 55 mm, speed of the shaft or shaft speed is 1800 rpm, inlet oil pressure is 3.875 megapascal, comma, external pressure equals 0, the mean oil temperature is 60 degree centigrade, oil used is SAE 60, full stop. The desirable oil film thickness is 0.0875 millimeters, full stop. Determine the load that can be supported by the bearing. Second sub question, the rate of oil flow through the bearing, and the third sub question is power loss due to viscous friction. So that is a problem statement given to us. Please check what is the difference from the previous problem to this current problem. So let us write the data as given. So diameter of the shaft 130 mm, we can write that as 0.13 mm. Diameter of the pocket is 55, which can be written as 0.055 meters. The speed is in terms of RPM. So let us convert that to RPS. So how to convert that to RPS? 1800 by 60, which will turn out to be 30 RPS. Supply pressure or inlet pressure is 3.75 megapascal. External pressure is 0. Operating temperature is 60 degree centigrade. Oil used is SAE 60, and the film thickness is 0.0875 into 10 power minus 3 meters. So what is the difference that you are seeing in this problem? The major difference in this problem is the viscosity. Unlike in the previous problem, they have not given the viscosity directly. They have specified the operating temperature of the oil and what type of oil is used. The type of oil used here is SAE 60, and the temperature at which the bearing is operating is 60 degree centigrade. Based on this, we are supposed to get the viscosity. How to get the viscosity with these two data? So we have the charts, or we have graphs to determine this viscosity from the data handbook. So you know the operating temperature and you know the type of oil used. So from data handbook, page number 23.7 and figure 23.2b. So the page number is 23.7, and in that page, so please refer to figure 23.2b. So we will be having a graph. We have a chart for this. Which says absolute viscosity versus the temperature, absolute viscosity versus the temperature, where the x-axis is the temperature and the y-axis is the viscosity in terms of millipascal seconds, that is 10 power minus 3 pascal seconds. And then we have a variations with respect to the type of oil. So it will start with SAE 10 and it will end up with SAE 70. So now the temperature given to us is 60 degree centigrade. So please check out 60 degrees along the x-axis. Check out 60 degrees along the x-axis. Yes, here I have 60 degree. Then move upwards till that 60 degree line coincides with that of SAE 60 oil. It will just touch up over here. SAE 60. So we will be ending up at this particular point. So from this graph, what I can say is we have for 60 degree centigrade, the viscosity of the oil will be 70 cp, that is 70 centipoise. From figure 23.2b, for T equals 60 degree centigrade and SAE 60, we get neta. That is, what is neta? Neta is the absolute viscosity. So absolute viscosity. For this absolute viscosity, we have from the graph as 70 Cp, which means 70 into 10 power minus 3 pascal second. 10 power minus 3 pascal second. This is the new thing that we are finding out. From the data handbook in hydrostatic bearings. Whereas in the previous problems, they were giving the value of viscosity directly. But in this problem, they have given the oil temperature and the type of oil. Based on these two data, we should find out the viscosity using the data handbook. Okay. Now the problem is same as we have done in the previous cases. The first one is the load. We know from page number 23.67, the load carrying capacity is given by W equals pi P naught d2 square minus d1 square, whole thing divided by 8 natural log d2 by d1. That is equation number 23.143, page number 23.67. Observe, we know the supply pressure, we know the diameters, and we can just calculate the load carrying capacity. Pi, the value of P naught is 3.75 into 10 power minus 3, d2 0.13 square, d1 0.055 square, whole thing divided by 8 natural log 0.13 divided by 0.055. So on calculation, we get the value of W. So the value of W will be 23.753 into 10 power 3 Newton, or W equals 23.753 kilo Newton. 23.753 kilo Newton. So we found the value of W, that is load carrying capacity. Next is the oil flow rate. Again, we know the expression for Q. Q equals pi P naught H cube divided by 6 neta natural log d2 by d1. Equation number 23.144, page number 23.67. pi P naught supply pressure 3.75 into 10 power 6 H viscosity is 70 cp. So let us find out the value of Q. Let us find out the value of Q. The value of Q, we will be getting it as pi into 3.75 E6 into 0.075 divided by 6. .1845 into 10 power minus 5 meter cube per second. The last sub question is power loss due to viscous friction. This we have as 0.062 n dash square neta divided by 16 h d2 to the power of 4 minus d1 to the power of 4. Equation number, page number 23.67. Equation number 23.145. 145 A 0.062 n dash square neta by 16h d to the power 4 minus d1 to the power of 4. So we know the terms. Let us calculate 0.062 30 RPS, that will be 30 square, 70 into 10 power minus 3, 16 into the value of H is 0.0875 into 10 power minus 3, diameter is 0.13 to the power of 4 minus D1 0.055 to the power of 4. We get the value of power loss in terms of kilowatts. Let us find out. T square into 70 E minus 3 . So we get the power loss as 0.7713 kilowatts, 0.07713 kilowatts. So observe, we have done the problem, and accordingly we have calculated the unknowns that they have asked. So you should focus on what's the difference from one problem to another problem. The major difference in this problem is, in the problem statement they have not specified the viscosity of the lubricating oil. We found the viscosity of the lubricating oil based on the temperature and the type of oil that is being used. Okay, that is the only major difference. The rest of the problem remains the same. So by this we have done around 6 to 8 problems on hydrostatic bearings. So the major important things in this particular module is the load carrying capacity, oil flow rate, are the major two difference, two important derivations that we have in this module. The next is the problems based on the load carrying capacity, supply pressure, oil flow rate, power loss due to viscous friction. And one more thing you might be asked is to find out the coefficient of friction. You know the coefficient of friction, mu equals frictional force divided by the normal load. You know how to get the frictional force. Frictional force is the ratio of torque to the radius. It is very simple. What is torque? Torque is nothing but force into the perpendicular radius. I want to determine the force, so I will just do the cross multiplication to get the force, that is F is equal to T into R. But here in this particular hydrostatic bearings, you should be very careful. The radius is not the outer radius, it is the mean radius. The mean radius. What is that mean radius? RM, mean radius, is the average of the two radius, that is the radius of the shaft and the radius of the pocket. R1 plus R2 by 2 gives us the mean radius. And how to get the torque? Torque is quite easy to get, because we have seen power from our basics of engineering till to now. Power equals 2 pi nt by 60, where n is in RPM. If you substitute n in terms of RPS, the equation of power will be just 2 pi n dash into T. When I use it is n, so you should divide that with respect with R60 to get the power in terms of watts. Okay. So I want to get the torque. Just modify the power so that we will be getting the value of T. Once the T and the torque and the mean radius are obtained, you can find out the frictional force. And we know frictional force, we know the load acting on the bearing or the thrust load. So take the ratio of these two to get the coefficient of friction. So these are the varieties of problems that we have in this particular module. So this module is quite easy, and you can score very good marks in this particular module, as we have very much less things to study here in this particular module. Okay. So we will meet in the next session, where we will start with module 5. Thank you.